Howdy, this is where Howie say hi in Texas. Um, so today we'll be uh, uh, learning together how to write a program in Julia. And first, let me introduce myself. My name is Jian Tao. I'm an assistant professor from the School of Performance, Visualization, and Fine Arts. I have a background in computational astrophysics, and I have been doing high-performance computing, parallel programming, um, data analytics, AI, machine learning in the last several years. And Julia is one of the languages that I find really interesting. And it combines both Python and many other features of some latest development of language computing, computing language. And it combines probably the best of multiple most useful languages you probably ever heard. And it's still developed, on the rapid development. And there is a company started to provide commercial support behind it. And there are a lot of applications built with Julia now. So today we'll first get you all started with our ACES system, and which will be the high-performance computing system we'll be using for you to practice your Julian skills. You can also install Julia on your local computer. After that, we'll get into some details about the syntax and how to write simple Julian programs. And hopefully in the future, we'll be offering some more advanced topics, but today we'll be focusing more on the fundamental building blocks for the Julian language. I'll just stop my video just to make sure that I don't have any network problem, and I'll turn on my video during the Q&A session. So we start with ACES system, and we learn a little bit about Julian, and then we get into some more advanced topics, to get you started to write some simple Julian programs. And then we'll learn some basics about plotting with Julian, which will be usually the most useful thing for using a language to do the scientific computing. Doing some visualization is important for you to see how these things are working. So ACES is one of our, I would say, one of our most powerful machines here at NM, and it's funded by Natural Science Foundation. For a traditional HPC system, this is more or less like what you will see in a traditional high-performance computing system. You have a network that connecting different nodes. Inside each node, you have like a traditional computer, in a sense that you have CPUs, you have memories, you have accelerators. Most of the computer you use might not have very powerful accelerators. Probably you just have a GPU just for visualization purpose, but you probably heard about NVIDIA, right? They have been making GPUs to speed up the computational process for a lot of computing intensive applications. So we call them accelerators for the reason because they help us accelerate the computation. FPGA is another kind of accelerator you can use to speed up your computation, but essentially, this is a traditional way of how high-performance computing systems are working. But again, there are different architectures, but this is the most popular architecture. Based on this architecture, there are multiple programming frameworks that you can leverage. The most commonly used one in the HPC community will be MPI plus some other programming language that you can use to help you speed up the processing. So MPI will be helping managing the communication between the nodes through the network, and CUDA, OpenCL, OpenMP, and others will be helping you for in-node management because those are more helpful for you to do utilize accelerators or using the multiple cores in the CPUs for multi-threading computation. So basically, this is an overview for traditional HPC systems with hardware and a software stack. Now, ACES is different in many ways. It's supported by a National Science Foundation, and it has been optimized to offer to offer the research community an accelerator testbed for numerical simulations and AI and machine learning workloads. This is a West Campus data center here at Texas A&M. So, with the computing power that you may heard about, we'll get into the details. But as you may imagine a big computing cluster, but actually the size is relatively small. And compared to some large computer centers you may have heard about. And ACES has been very, very, in a sense, computing power is very condensed in a sense that it's able to push a lot of computing power inside those accelerators. And the total physical size is actually much smaller than some traditional computing systems if you're purely based on CPUs or some other not so powerful accelerators. ACES has been designed to serve simulations and numerical simulations and AI and machine learning applications. So it has multiple purpose into the design of itself. So the CPU-centric computing, we do have some nodes with big memories and a lot of onboard high-speed storage. And of course, we have NVIDIA Mellanox InfiniBand connection between all the nodes. For composable infrastructure, we have reconfigurable infrastructure that allows up to 20 PCIe cards. You could have 20 GPUs interconnected through this interface. So there's no way you can get a single computing node with 20 GPU card in it. But with this composable infrastructure, it's doable. And you can mix up your GPUs FPGA depending on your application. And then this infrastructure makes it possible to do this software configuration. The data transfer nodes are available for you to transfer data to the outside. We have 100 Gbps network adapter available. This is a list of all the accelerators. I won't go into the details, but the one we'll be using for today's short course will be mostly on the CPU side. If you're taking the GPU course and CUDA course and some other courses, you will be using those GPU nodes. And there will be other short courses covering different accelerators. And some of those are very, very new in the market, and that gives us a fabulous testbed for a lot of new algorithms development and the new library development capabilities. So there are multiple applications could be supported using all this, and also the corresponding libraries. And I'll just leave it here. I'll not go into the details, but you might see there are different kind of accelerators we are supporting on this system. So essentially, we have login nodes, and user can log in and to get your code compiled and tested. And then you can submit your job to the background computing nodes. And depending on the job configuration, you can choose the particular accelerator you want and particular combination of particular combination of accelerators you want in your job script. So getting access to ACES, the easiest way is to get, not easiest, probably you need to have an ACES account. ACES is a new version of XSeed, which was back then many years ago called the TeraGrid. It's a networked computing resources providing free computing resources for researchers in the US mostly. And ACES system is a part of this ACES network. You needed to get an account at ACES, and then when you're writing your application, you need to pick ACES as part of the as one of the machines you want to use, have access to, and then we can get you started on the system. So we all need a PI. If you are undergrad students, you'll have to go through this with your PI. And also graduate students can directly apply with their PI, but you need a a little collaboration from PI to use the system. So always a probably good idea to talk with your supervisor or your advisor or anyone in your department who might be working on a course or any projects. And if you want to join them and work with them, you can get access to the community resources if they have access to the server. To run your jobs on ACES, and just like running on any other shared systems, you need to get into the queuing system. So there's no way that the system can just be there, just on demand for everyone, just because we have limited resources to share. The queuing system is more or less like the queuing system when you get into a supermarket and try to go through the register, and get in the line. You need to have access to the front end, that's a login node. And you need to get your code either compiled or tested and on the login node to make sure your code is working, because the login node will have the similar hardware profile and the backend. So whichever you tested on login node will be guaranteed to be working in the backend. So get your code tested on login node, and then you can submit your job through our queuing system. So I'll get into some examples here, but you can refer to the HPRC short courses on the queuing system and HPRC introductory courses to learn how to use the queuing system and to use the system, other systems hosted by HPRC. So particularly, let's get back to the ACES system. To get access to ACES system, you can log in through the terminal if you're familiar with Linux command line interface, or you can use the HPRC portal. And what you can do when you get to the HPRC website, there is a drop-down menu called portal. You then just click ACES portal. It will lead you to the particular page. And you need to log in, get you authorized, and you get to the system. So this is what it looks like. I'll show you one example. Don't worry too much. If you are using this ACES, you have used ACES before, this should be straightforward. If you have never used it, you need to at least get an account, register, and then get access to it following the authentication system ACES. Before I move to the shell here, I'll show you one example how this will be working. Let me see. So this is our HPRC website, and there is a portal drop-down menu. If you move your cursor all the way down to ACES portal, you click it, it will point you to the, I'm sorry, already logged in here. I probably need to log out. I just want to show you all how the whole login process is working. Hopefully, it's probably successful logging me out, because I might have my session activated, so that will be storing. Okay, never mind. So you can log in with your credential, and this is what you will see after you log in the ACES system. So we have this ACES on-demand portal, which provides integrated front end for you to check your files using the file menu. You can go to the corresponding directories. You can check your jobs and look at other features provided job menu, and then you have access to the shell access, which is a web-based terminal, and give you the access to the machine using the command line interface. So there are some other interactive apps. If you're using different applications, you can use them directly. And also, there are some other features you want to look into yourself. But today, what we'll be using today will be the ACES shell access. So if you go to clusters, the drop-down menu, and click it, it will point you to this web-based command line interface, which is very nice. It has all the highlights and all the features we need. Now, before we switch back to the slides, I want you all to look at this. This is a very first thing you see when you log in our ACES system. You have some general information about HPRC, and there are also some links for you to have access to corresponding documentations and also the YouTube channel, which has a collection of all the videos recorded for short courses and some introductory materials. And also there are some important policy information you need to be aware. Every time you log in, this will show up, so you won't forget about it. You just need to be aware that this is a shared resources. You need to follow all the rules here. And then at the end, there will be some updates about the latest update about our server. If there's anything goes wrong, you'll get to know information here. If the system has the periodical updates, maintenance, and there will be some schedule showing up here as well. At the end of the screen, you'll see this quota. Basically, that's my quota. Basically, on my home directory, I have a disk usage of 7.9 gig. Zoom in this a little bit. I have a limit of 10 gigabytes of storage, so I use almost 80%. It also keeps track of how many files you are having, because for the shared high-performance system, the number of files actually matters a lot. So some people used to have a big files, some people used to have a small file, but many, many, many files. When you're getting more and more files, the system will have a big load, even though every file is small, but it still is a big concern for the system. So that's why you have two limitations. One of them is the limit of size, another one limit of numbers of files. The number of files is important because for Julia, when you try to install the packages, those packages will be, sometimes it'll be small, sometimes it's big, but just like an Anaconda, when you install Anaconda, there's so many small files, and that you can easily fill up your quota on your home drive. So that's why when we try to install Julia package and other two, potentially if you are using Anaconda similarly, you need to set your directory where you want to install your packages under the so-called scratch space. The scratch space is not literally scratch. Basically, we are not throw everything away from you. There will be some notification before we needed to purge our scratch space to empty space for future jobs. So the scratch space, I have 1 terabyte of scratch space, high performance scratch space, and directly connected to our computing nodes. I only use the 60 gigabytes of it. And the total limit of file here, it's about 250,000, which is more than sufficient for most of the applications you might be dealing with. So that's the login interface. Let's get back to the slides. So this is what you will see after logging ACES system. And now, because installation might take a while if I've never used Julian, because some packages might not be pre-installed, so we need to install some packages. The module itself is preloaded, it's pre-installed. You can just load them just like many other tools you are familiar with. And let's go through this quickly, and then I'll get back to the command line and show you how to run that. If you want to install Julia directly on your home directory, which is also scratch space, you don't want to install anything on your home directory unless there's some important file I want to keep there for longer term. You can go to the Julia website and download the zip file. It's tarball. It's a gzip file. You can untar it, unzip it, and you can save it into a temporary, scratch space, and then you can use it directly there. This is not recommended mainly because you need to keep track of the versions. It's kind of not so easy for you to get this down for new users. The recommended practice is to use a pre-installed Julia module. But again, because sometimes we might not be catching up with the latest release, and you want to use the latest version, you probably want to just go to the website, download the latest version of Julia and try it out, or even some developed version. Because on our system, we only installed the release the stable version just to make sure we don't have any actual issues to worry about. So after you get Julia started, you can start installing packages. So the very first line here, the export Julia deport path equals to scratch, etc. It's just trying to tell Julia installer that we want to install all the Julia packages under the scratch space and under the directory called the .julia. Everything with a dot, starting with a dot, will be a hidden file by default. So you won't be able to see that directly unless you use some special options to show the directory. So by default, you won't be able to mess around with all these dot files. Those are hidden from you. And then you can start your Julia and then start doing the installation. I'll go through this process with you all, but probably it's good to keep this to the left or side of you so that you can copy and paste this easily. This is what I'll do here. I'll just copy this one, and then I'll go back to my shell script, shell interface. So what I'll do next, I'll first do, I need to load my Julia module. So you can clean up your interface. So currently I'm under my home directory. If you do pwd, that's where I am. You can cd scratch. This cd, you can use a tab to autocomplete. So $scratch will be pointing to your scratch space, which is a default system environment variable pointing to your scratch space. This is my current scratch space. That's where I install my Julia packages or other things if I need to. But now I'll show you how to load the module. To load the module, if you don't know what the module name is, what you do is to do just module spider Julia. This will show you all the Julia modules already installed in our system. Of course, like many other things, there are a lot of shortcuts make life easier for you. You can simply do module. I'll start with a harder one or longer one. You can do the module load. You can copy paste the last one here. It's a 10.2. It's probably the latest stable version. You can use a Control-C, Control-V on my Mac, but you may have some other. You can use a middle. If you have a 3-key mouse, you can use the middle one to paste this selected string, assuming you are already familiar with that. This is the way to do it. So after you get this done, you can check module load. I'm sorry, ML. This will show you what's the module, module loaded currently. This means I have this module already in my environment. All my paths are already pointing to Julia's corresponding libraries. Now, if you want to check which Julia you are pointing to, which Julia will show you which Julia you are using. Sometimes if your environment variable got messed up, even though you loaded the right module, but your executable might be pointing to some system installation, which definitely is not the way you want. Just to double check, you can double check your Julia installation is the right version here. Now, I'll show you the easy way. If you're new, let's go back to clean up our environment. To do that, you do module purge. This will clean up your computing environment. So if you do this module load again, there's just no module loaded. Let's clean up our screen. Let's go back. So, like I just mentioned, module load is just a ML is a shortcut. Our admin created. Probably it's also by the module developers that created a shortcut called ML. It's like a module load. And then if you don't know your particular, for first users, for beginners, you just want to use the latest Julia. This is the shortcut we created for you. It's not recommended, but it doesn't matter for this introductory course. It makes life much easier for everyone. So by default, by ML Julia with a capital case J, you'll be loading this latest version. That greatly shorten your typing here. And with that, I can just type in Julia because Julia already loaded. I'm running Julia now. So for installing any packages, I remember we needed to export the particular directory. So Control-D will exit the Julia shell, just like a Julia repo. I'll get back to what the repo is. It's, get into details, but we are just exiting this Julian interface. One thing we need to do is that we needed to copy and paste. Oh, sorry. I think I needed to go back to copy and paste the export command to make sure my Julian installation understand the particular directory I want to install my packages. Okay, I copy this statement. Now, what I did here, I created a system environment called Julia default path to point into the particular directory. If you do this echo, this will show you what this path is pointing to. This is what I was trying to create. Okay. Now, whenever I get Julian installed, Julian started and start ending any packages, it will be directly installing all the packages under this directory. That's called a Julia default path, more or less like your warehouse. That's where you store your Julian packages. So let's start Julian prop again. And you can use a right square, or how to call it, right square parenthesis to get into the package shell. This shows up whenever I click this key. You can use a backwards or delete key on Mac. I'm using delete key on Mac to go back to my Julian interface. If you use a square bracket or square parenthesis, right square parenthesis, you'll get to this packet shell. Now, you can install the corresponding, this is, I just use a Control C to copy this command here. I can install plots, Unicode plots and Plotly and all those libraries to my system. Depending on, I probably already have everything installed, it's probably easier. But if you don't have anything installed, it will take a while for it to install. So I'll let you all get everything running so that we can get back to the slides. Hopefully we can get this working. Okay, I'll go back to the slides. You can keep this running here. So again, the first export text Julian, the warehouse. And then you start Julian and do the installation. The installation will automatically install everything under that directory. So you don't mess around with the quota, etc. Because the scratch space has a much bigger quota space for you to play with and higher file number limitation for you to install more files there. And after that gets installed, we'll get into the scratch space and the copies examples. We'll go through this later on when we start running examples, but we can stop here. So to load module, compile, and run, we have already done that. And it's more or less like what we have done. Just showed you all. You can get this started. So to get started quickly, we are using so-called a REPL. That's the one I just showed you all. It's called a REPL because it's called a read, evaluate, print, loop. That's what REPL stands for. R means read, E is evaluate, P is print, and L is loop. The packages are all installed in your warehouse. That's the default path you set. So that's why you need to export the default path so that Julian executable understand where the files need to be installed. You need to do that first before you start doing the installation. Otherwise, you can easily fill up your home directory, but it's fine. Just remove .julian and then just redo it. Okay. Now you can show the version information. These are built-in functions you can directly call it. It's just like Python. If you're familiar with Python, learning Julia is almost trivial. There are a lot of fancy features you can utilize, but essentially it's just like Python with some extra, fancy features. And it does support Unicode, which is quite impressive. The reason, I can probably show you here. Let me go back to the command line interface. Okay, now it's done. Let's go back. And then I'm on Julian, so I can use a remember tab is your friend, which is make your life much easier. You can use a tab key to autocomplete. So this print out the Julia. As you can see, the library, the Julia default path is already set here, which is very important. Otherwise, you again get the quota errors because you use up all your quota. And then now this is something I want to show you. If you do this and a tab, it'll use a Unicode, which will be translating into an internal function, square root, and then it will take your input and take a square root for you. I'm not sure what is there is for I in what's the example I have here? I just want to exactly matching what I have there so that you can 1 and 10 print line. Okay. I think it's I needed to make sure print I and end. Okay, I'm sorry, there's end. So now look at this one. If you're familiar with all the state you're learning algebra introductory course, this is a yin symbol mathematically. So all this could be translated into syntax that Julia can understand, which is quite impressive. Make your Julia code more and more like mathematical expressions you're writing directly. So that's just starting. Get your, see what Julia can do like in a different ways. I don't know. I'm not catching up with the latest development in Python in the latest version, but it might be able to support this as well. But I don't know. It was not working when I tried it, a while back. But there are some keyboard. I'm sorry. There are some command line controls like shortcuts you need to learn, the key bindings, which will be relevant to your repo itself. So it has nothing to do with the Julia. It's just a repo, give you some shortcuts for you to do things separately. You can use Control D to exit, Control C to cancel and interrupt when you have any calculation going on. You can use the Control L to clean the console screen. There are many other things. For example, the one I used is the packet. When I try to install any packet with a right square bracket, you can use this to enter the packet repo. You can use the backspace to go back to the original repo, or you can use a shell repo, help repo. You can use a question mark or semicolon. You can, and it's more or less like getting into using the help function to answer your online, give you some online documentation. I know we spent a bit more time in part 1, but part 2 we can go a bit faster because for most of you who have any programming background, this part is just almost trivial. And not this part, also the next part. And the thing is, it's get you all familiar with the flavor of Julia, and of course, get you all started on our system. And the hope is that you'll be using Julia to do large-scale parallel programming in the future, hopefully. And then you can leverage all the accelerators that we are providing to help you with your computational task. So Julia was started as a teaching language in MIT, and just like many other languages, it started by, for educational purpose, Pascal. I'm not sure if Java was like that, but Pascal definitely was Pascal. What others? Logo and TurboLogo and those tools have been designed just for teaching purpose, but it turns out those tools have been very powerful. And Julia have been designed to be a language for high-performance numerical analysis and computational science. But people are turning Julia into a more general language, kind of like a Python in many, many ways now. So you can use Julia to do a lot of things. And it combines the features of Ruby, MATLAB, C, Python, R, and others. And the first release was in 2012, even though it's a new language, but still 12 years old now. And the latest one I just checked, last month it's at 1.10.0. That's the version you are using today on ACES system. So the website I mentioned, the official website is julialand.org, and it's customized for greedy, unreasonable, demanding programmers, which is exactly the reason why you are here to learn Julia, right? And Julia Computing is a company started in 2015, and Julia is getting really popular in the scientific machine learning community, and there have been a lot of work in that direction. There have been a lot of development along that line as well. So this is a Julia micro benchmarks showing the performance of Julia. Again, I already mentioned that Julia is kind of like Python, but it's faster than Python. For any code written natively with Python and natively with Julia, Julia is faster, mainly because Julia has a so-called just-in-place compiler. So then, whenever you run Julia, the Julia code will be pre-compiled internally, and it will be then executed. So the performance definitely will be better than Python because Python needs to be interpreted step by statement, unless you have some other tools to speed up Python as well. So, but if you just directly compare Julia and Python coding, natively written in those languages, Julia is definitely faster in many ways. Now, using a C program language as a benchmark, because C is more or less like a standard for benchmark testing and many other things. If we consider C is 1, now we run the benchmark, the micro benchmark, all the like small benchmarks on different languages, you might see the performance dramatically different. If you compare C and Octave for running some applications, Octave, which is kind of like an open source version of MATLAB, it's much slower, which is Octave is the one on the very right here. And Julia actually is able to beat C in certain applications, mainly because for certain applications, the particular way how the language got designed, the cache reusage, and the data transmission got optimized, so it can even run faster than handwritten code. And Julia has this built-in called a just-in-time compilation, which is able to optimize your code in a way that it's kind of hard to optimize manually in many cases. So again, this just trying to show you that Julia actually is very fast if you write it in the right way. It's kind of like a CUDA for GPUs. If you write it in the right way, your GPU code will be faster. In other cases, you actually get a slower code if you don't write your CUDA code properly. So this is the latest RedMonk programming language rankings. So the x-axis, the horizontal one, is a popularity rank on GitHub. It's how many stars you have. It's more or less representing how many users you may have. How popular you are for this open source community. The vertical axis shows popularity rank on Stack Overflow. That's where you start asking your questions in different languages on different technical area. This also represents the popularity for certain languages. As you can see here, I highlighted some of those with red underline here, showing those languages. And we have been teaching here at LM. We have been teaching Fortran, CUDA, Julia, Python, sometimes C++ even. And then, as you can see here, Python and JavaScript, and those are very, very popular, mainly because the web development, right? That's very a lot of money coming in for the programmers. And then you have a Julia actually getting pretty popular. It's even more popular than Fortran and CUDA, which is understandable because Fortran is gradually, I'm not saying phasing out, but it's getting less and less popular on the general programming side, generic programming side. But Fortran it's mostly focused on computational stuff. And the CUDA, it's also you have similar amount of questions and topics, but the users seem to be not so many compared to Julia. But again, this just shows one perspective. These are just two websites, GitHub and Stack Overflow. It doesn't really represent the whole status, but it gives you some idea about how things look like. So Julia is fast. It's a general programming language. it can do the dynamic typing. It's not like a C or C++. You need to declare your variables and before you start using them. And Julia doesn't need to do that. It automatically type your variables. And also Julia, as people consider, it's like a programmable as Python, and it's as fast as Fortran for numerical stuff. It's like a Python on steroids, and that's what I heard from a user a couple of years ago. And it's very popular in the scientific machine learning community. If you are not familiar with scientific machine learning, that's a field that's trying to use machine learning technologies to solve PDEs, ODEs, ordinary differential equations, the partial differential equations to simulate the physical or mechanical world. So scientific machine learning is targeting that particular area. So there are multiple interfaces that you can use to develop Julian. Juno IDE is based on Atom. I believe that's pretty popular. The IDE framework that people have been using Atom to develop different IDEs, and this is one of them for Julia. You might be familiar with Jupyter Notebook, but you're probably not familiar that Jupyter, this J here, J here represent, stands for Julia. No, I'm sorry, JU here, no? JU here stands for Julia. So we have a Julia, Python, and R. So this interface, this Jupyter Notebook was designed to serve three communities: R developers, Julia developers, Python developers. But again, the most popular community, as you may imagine, that's Python community. Almost every data scientist started by learning Jupyter Notebook. Nowadays, the Google Column3 is another way to support. I'm not sure Google Column3 will support Julian, but you probably want to look into. There might be ways to do that. So the interface we'll be using today, and very likely in the future when you want to do some interactive development, you probably want to use this repo as well. So repo stands for read, evaluate, print loop. It's just keep iterating. It's keep running, and it will just like a Python command line interface. When you type in a statement, it will run it and give you the output, and then you keep doing this. Okay, let's jump directly to part 3 because all these are connected. Just like many languages, the very first thing you do when you learn a language is to try to use it as a calculator. That's what I learned almost all languages. Just get it by putting numbers. And I usually just put a very big number to test the limit of this particular language. I just put in say 69 factorial to see how fast it will generate. I use test my calculators using that 69 punctuate 69 factorial. I'm sorry, it's but usually for most of the old-fashioned calculators, it will fail to go beyond 69. 69 is the maximum you can get. That's usually I use to test the performance of calculators. Just like many other languages, Julia supports standard arithmetic operators. The exactly same rule you learn in elementary school will be applied here. You might not be familiar with mode here, which is just getting the to see if this one to divide to wholly divide a number by another number, and then you get the residue here left for you as a return. So everything else will be just following the same priority rule. You probably learned if you want to make addition before multiplication and power, you need to put a parenthesis. The same rules apply here. There is everything else will be almost identical to what we learned before for other languages. The only difference will be that the Unicode will be supported here as operator, and we can learn more about that later on. It's just quite amazing to see how that will make your program look more or less like art, like a mathematical paper. There is one special feature that added here. It's called a dot operation. So you can have A plus B, and then you can have A plus dot B, which extra dot operation to your operator will make it possible for you to do this element-wise operation for your vectors, matrices, etc. So we'll get into detail about this dot operation. The dot operation is like I would say like sugar syntax or syntax sugar. And you can add to your existing syntax and make your programming much more interesting and fun to play with. That's probably one of the beauties about Julia, which is full of this kind of like syntax sugars and make you feel very comfortable when you're writing programs. If you're familiar with all the mathematical expressions, it's just getting to the point that programming language should be a language for math, and especially for these packages like Julia designed to do the computational stuff, right? And there are also the numerical literary coefficients are already pre-building and like many other constants you can directly use. And also if you don't have any dot operations, if you have a numerical value in front of variable, by default it will automatically assuming that you want to do multiplication, just like a for a, we know it's 4 times a. We don't need to put a times or a star in front between this 4 and a, and Julia automatically converts that into 4 times a underneath. So these are some simple expressions. You can try them out, and nothing fancy here. The only thing I want you all to see, I think there's something I want you like a Euler. You can just use a Euler number with a backslash Euler and a tab. You can convert that into the natural number. The same goes for pi. You can use pi, and in Greek pi, and it will be representing the particular value you're talking about. And it can be to arbitrary precision, which is quite impressive for Julia. And we can talk, we have a couple more slides about the precision for all the numbers. And this is another nice feature for Julia to support arbitrary precision calculations. These are also standards for relational operations. If A equals B, you get true value returned by the comparison. It doesn't really give you any numerical value. This is just Boolean values, true or not true, which is the false, right? True or false. That's the two options. And also you have not equal to and greater than, less than, greater equal to, less equal to. And you can also use nice symbols like not equal, backslash NE at a tab will give you not equal symbol. And then less than and greater than will also give you different symbols that you can make your code look more relevant to your mathematical equations or formulations. These are Boolean bitwise operators, and if you have all the logics like Boolean values, true or false already calculated, then you can use this to do the operations for those Boolean values. For cryptology, for cybersecurity applications, we need to do some hashing and try to do some code cracking. You might need to do some shift, which is just a bit shift. Whenever you do the shift right left, you move your you shift your bit 1 bit, more or less like multiply by 2 or divided by 2. But those are not commonly used for most of computational calculation unless you're dealing with some specific application that you need to deal with bits. In many cases, numerical calculations, you don't need to deal with those. None and infinity, they are treated differently in Julia because infinity itself is treated as a more or less like numbers of not nines. When you're dealing with infinity in other languages, it's treated as not a number. So here, not a number itself is not a number value, and it's treated in like a special way for you to do some debugging and other things. And infinity itself could be representing a number, but this number is just so big you cannot represent it with current hardware resources. It's just infinite. Infinite itself, you can treat it more or less like a number itself, like 0. You can treat it. No, I don't mean it's a 0, but inside Julia, it's treated as a number. It's not a none is an error. is an error that the system can capture. And but an infinity here is treated as a number in Julia, which is a kind of different. Okay, so variables are, there are 4 or 5 types of variables, basic types, like float. That's just real numbers. Regular real numbers, you can use a float. You have integers. You have char, which is just individual characters. You have strings, which is a like array of chars. You have Boolean values, true or false, only 2 values, Boolean, bool value. So global variables cannot be deleted, but you can you can clean up the content of the global variable with the keyword nothing. And Unicode can also be used as variable names. Like here, I have several examples here. And a variable info function, the second line in this code section, the variable info shows you some information about variables you already defined previously in this in the particular session you're currently working on. And at the bottom, you can have a football. I'm sorry, if you want to have this emoji, you needed to have a colon. I just trying to try this, but I forgot to put in colon here. You put a colon, football colon, and a tab, you'll get a football icon printed out, which will be treated and used as a variable. For the machine, it doesn't really make any difference. Think about it. For B here, B itself is entirely treated as some numerical value stored, representing the particular variable. It's just numerical value, but we can see it's B because it's printed out as a B on our screen. The same goes for this football icon. Internally, Julia is treated more or less like a symbol referring to a particular memory address. And now, to us, it's just a symbol. It doesn't make any difference on the computer side. So this gives you a very nice way to, write programs. But I don't see many programs written, using this icons. But it's kind of fun to see how this kind of programming interface will be evolving in the future, and how this could be helpful for teaching and educational purposes. Naming conventions for variables. You cannot use numbers at the first at the very beginning of your variable, which is following the traditional way how these Unix variables are defined. And also in Julia, like a for C, which is interpreted as a for times C, and it might be ambiguous to put a for C here. But you can use underscores and underscore at the very front, but you cannot use numbers. You can also use the Greek letters and also symbols like that, but put a numerical value at the very first front of the variable is a no-no, not only for Julia, but for many other programming languages. And also Julia is case sensitive. Capital A and lowercase a are different. It's just like Python. You don't want to mess around with different cases. To display a variable, you can simply print it, or you can use a print line. Print line it's just like print, but add an extra line for you. In some languages like JavaScript, they do have this to help you to, without you insert any break or any new line symbol in your sentence, making your code cleaner. It's also helpful, for debugging purpose. You don't need to worry too much about inserting lines here and there, and it make it easy for you to see the comments or output directly. Okay, so this is a very quick exercise for you to get started. Let's say we want to create 2 variables. You can simply create 2 variables by typing a equals 4, enter, and b equals 17.2, enter. Now you can just use this a and b to do some calculations. I put 1/3 here as a special symbol. Actually, you can make that happen with a 1/3. I believe 1/3. Use a fraction. You can probably show this 1/3 power in a way how this looks like. But again, this is the way how you use computers to help you to store the data into memory. The memory, 2 memory blocks here. So one is called A, another one called B. And then all the rest will be getting the number from the particular memory location, and then utilize the information to calculate whatever you put in there as a formulation. More or less, you consider the first, those are A equals 4 and B equals 17.2 as initial condition. Whatever you do next will be utilizing the information to move to the next status, to next state of your system, assuming your system relies on those variables. But we don't have any functions defined yet. With a function, you can have some modularized way to do those calculations. You don't need to type this anymore. For example, A not equal B. This you can write A not equal B and a function. This function will take A and B and the input and return a Boolean value and the output. You can write a function. You can start put functions together, functions of functions, and then you can build modules. And then you can use modules to build even more interesting applications. So like hierarchical structure, but everything starts with variables. You define variables, give the meaning of the variables, and then you can start building out sentences, statements, and gradually you build up your application. So these are some basic syntax for statements. We start with, comments start with a pound sign, and anything sign pound sign will just treat it as a comment. So the interpreter will not just discard it. And when you're putting this into a script, Julia script, the interpreter will discard all the, filter out all the sentences with a puncture, start with this symbol, and then you can have multiple expressions together with a begin and end ramper, or you can use parentheses. It's just like different ways of writing this, putting different statements together as a ramper. So when you write down the equation, the statement like this. So Z will be set to the value after you finish evaluating all these three statements. So when x equals 1 and y equals 2, you get x equals y. The returning value of x equals y, x plus y will be returned back to Z. So Z will getting 3 here. Even though this is doable in Julian, but in many cases, this kind of statement is kind of confusing, not only for beginners, even for experienced developers. You don't want to show off your programming skill by just putting all this fancy statement together in a way that's not easily understandable. Readability is always the highest priority when you're dealing with real-world projects. And for some people, this is readable, it's fine, but it's probably better just write down your code just like x equals 1, y equals 2, and z equals x plus y. I would be preferring that way if I'm reviewing the code myself. But again, what I want to tell you here is that Julia support all this. It's doable. It's just like you need to be cautious about how you want to utilize this in your production code. So you can have optional semicolon, and if a new line is used, to separate a statement into, it's good to have a separator, more or less like a semicolon, to tell you that these are different statements. For numerical data types for Julian, we have, again, we started with real numbers, then you have multiple real numbers put together, you have complex numbers, multiple, just two of them. You have a real part and an imaginary part. You get two real numbers together, you can construct a complex number. And for real number, you have abstract float, you have integer, you have irrational number and irrational. And irrational number here is the fraction. The fraction could be represented as an exact number here, like 1 divided by 2. In Julia, 1 divided by 2 is not calculated until you want it to be calculated. So 1 divided by 2 is 1/2, but in Julia understands that you're doing you're defining a rational number here by giving this this denominator. It's have a combination of denominator and denominator. When you evaluate it, it will be evaluated to the precision you need. But before you evaluate, that's an exactly perfect number. You don't have any numerical, errors introduced by evaluating the fractional number, which is, some nice feature. But again, it's introduce some extra burden for the system, right? For Julia. For integers and floats, you can have a big float and a big integer, and we'll talk about that in a second. And you can also add signs to integer because sometimes you don't need a sign, so you don't need negative sign for integers. You just want to go from say 1 to a very big number. You don't want to have negative signs. That's unsigned integers that you can define. So that's basic numerical data types. And most important for Julia because Julia is designed for do the computational stuff, and these are the basic data types Julia has, will be playing around and will be dealing with all the time. If you look at the data types, the smallest value for integer 8, it's 2 to, you have totally 8 bits, right? The max number you can get is a 2 to 8 number of, total. The max number you can get if it's an unsigned, it will be 2 to s. The reason because 0 is separate. So that's why the largest value you get 2 to s minus 1. You cannot get to 2 to s because that will go back to 0. That's the way how it works. That's binary numbers. Now, given 16, the max number you can get is 2 to 16. That's easily understandable. With 32, you get 2 to 32. That's max number you can have with 32 bits. For Boolean, it's straightforward. It's just true or false. 0 or 1, nothing more, nothing less, just 2 numbers. That's all you can have. To handle some big integers, which is actually kind of necessary nowadays when you're dealing with, a large number to decrypt and encrypt, and those will be dealing with a lot of integer calculations. And sometimes you probably need to go beyond the maximum limit you may have for the given data type. So there is a special data type called a big integer or big int for short. It's designed to handle big numbers. Here I have the big float will be handling big real numbers, and the big int will be handling big integer numbers. Okay, let's see if we can do this quickly. I'll just show you one example. Okay, now we are on Julian. Let me. Oh, when I drag it out, it will be out of my shared window, so I won't be able to do it. So let me. This is the only one I needed to copy. I think that's integer 6. So we want to see what's the 64 integer. This is the largest number that you can handle with integer 24. Let's see if you'll be unsigned on what is unsigned integer? It's a u. Let me see what's the u integer uint 64. Okay, uint 64. That's the max for this one. Let's do the 64 here. That's a number we can read it, but that's represented in the decimal values. If I want to do this +1, what do you expect it will give me? Okay, this is not a math or magic. This is just how the binary system, a number system is working. Because whenever you increase 1, it will go back to like a circle, right? Go back to another value. So this extra digit you're adding will be added will make this whole number get to a negative value. That's +2 here. It started decreasing, and then give a very big value. It'll start calculating, etc. It doesn't really matter here. So what I want to say here, so we want to have a number which is my x equals to this number, and whenever I do some calculation with my x, I will be in the danger to getting the wrong results, right? Now the thing is that if I want to do this, the best way I wanted, the with the Julia, I can handle this by using this big function. I think a big int. Let me double. I'm sorry. Sometimes I forget the. Um, I think it's just big, and that's all I need. So with this, I do the typecast on my x from integer 64 to big integer. Now I can get my results correctly. I can even do this. So you'll know this is the tens power of this number, right? You may be getting crazy. That's 100th timer, 100th power of my biggest number x. X is this number. By converting this x into the big integer, you can handle extremely large numbers. Not sure my computer might not be able to handle this. We'll see this. Okay, because I'm running on ACES. So ACES is huge, has a large memory, so it's able to handle this number of with 1,000 powers. But you can check how many digits this one is. You can count. I don't have time to count here. You can count how many digits this one maybe handle. But again, that's giving you the power to do the same, to do this. So that the same goes for big float. Before we get into big float, I have a very, very simple example for you to try out here. For example, if I define a equals to 4 divided by 3, that's a rational number. That's a rational number, right? Let me go back to, okay, a equals to 4 divided by 3. Because I already did the calculation. B equals to 1. Okay. A minus B will be, let's put C here. C equals to, so C is about 1/3, right? Now C times 3. Remember, if I do this and minus 1, this will give me the error I'm getting. This is a numerical error. That's error no one can avoid if you're doing numerical computation on a computer. Because with by default, I have probably 64 bits to represent my value. This is the smallest error I can get with 64 bits. That's the double precision number I am using. So because my real numbers were represented with 0 and 1s, and we don't have unlimited 0 and 1s. That's why we are limited to this precision. That's something you need to be careful when you are doing calculations, especially when we are dealing with numerical computational stuff. If you accidentally put this kind of number in your denominator, you need to usually good idea to add some floor value like 10 to the minus 6 or 10 to the minus 7 to make sure your value is not blowing up if you put this E value somewhere in your denominator somewhere. So that's usually a good practice to check to make sure you don't have this kind of issues. But again, this is a problem with a computer we are using on a daily basis. That's an intrinsic problem because the way how we represent floating point types with 0 and 1s. Now we can handle this with Julia with a bit more elegance. I'm sorry for my English, and then we can use big to convert this into a big float, and we can get to a very, very small error. And you can set your precision to an even larger number. You can turn this to extremely large precision. And then you can check error again to see how small error you can get. Let's take a short break. We'll get into the other data types, and then we'll wrap up this section and get into some Julian programming part. Okay. Okay, let's get back to Julian. So this is one example that you can deal with. At least, it's not completely resolving the problem, but it's just some way to mitigate some damage you may consider might be needed to handle for certain applications. But in most applications, there are always some tricks to go around with this problem. But in some applications where the precision is a primary concern, and you want to get to a point that the precision is high enough, you want to set the precision, and then you can use Julia to handle this quickly. Python also has similar packages. In C, there is also a module that can handle large numbers and with high precisions, but those are extra libraries, and you need to call those functions to generate those numbers for you. And this is a built-in for Julia. You just need to change the settings for the precision that you use to represent your numerical values. So complex and rational numbers, I already mentioned the rational number here. If you just directly use say 1 backslash 1/3, it will get 1/3. Just Julia will automatically do the calculation for you, 1 divided by 3. But you have a double slash, for example, 1/3, then you get a rational number. And you always have 1 or 3 there instead of 0.3333, whichever. So in some sense, Julia is saving both numbers for you. So it will do the calculation whenever it's needed. And then whenever you set your precision, this calculation could be done to follow your precision you set. If you don't do that, the precision will be calculated whenever you get your number represented with a floating point representation. So these are some useful functions. These are all usable for all numerical data types, and you can directly apply this to your program, and they will be working just by default, like what it should be. Char and strings are kind of different. These are mostly handling with text processing. And with large language models and many other machine learning models dealing with text processing, and Julia can handle that just like in Python. And also Julia can handle that efficiently as well. If you use a single quote for the string, or single quote for the character, it's treated as a character. And if you double quote for the character, it will be treated as a string, but with a length of 1. So you might consider 1 like A now. It's just a char in C, or just a single character. But a B will be a list of a list of character elements, but the length of that list is 1. So they are different, essentially different. More or less like when you define a NumPy array in Python, you have you have a 2-dimension defined, but the second dimension is just 1. Even though it's a 1-dimension element by itself, if you look at it mathematically, but you can define it as a 2-dimensional array. And it's kind of similar idea here. You can use string and length as the parameters, and you can evaluate those. And there are some built-in functions you can play with strings and others. To get to the element inside the string, it's just like a play around with element inside the Python list. And you can directly refer to the particular index and get to the particular element. And that's how you do the subtraction, do the, do many other things with all the string element. And a string could be, you can have internal evaluating string that you can use a dollar symbol. If you are familiar with LaTeX, kind of like the way how you buy LaTeX, you're telling LaTeX parser that you have a LaTeX mathematical formulation inside. The same here. If you tell Julia statement that this is a mathematical evaluation, do this evaluation before you output your final string for me, and it will do the evaluation first before it output string for you. So this is one way to write a function, and there are multiple ways to write a function. This is another way to write a function for you. There are many other tools that can handle strings. It's mostly about to find where the index is and how to cut part of the string and how to connect the string, how to divide a string, to parse a string, and doing all other stuff. And the Julia also support regular expressions, which is some of the most powerful tools you can use to parse strings. And before the large language model is able to handle all the interpretation for you, and previously, when you want to understand or try to do any parsing and try to extract meaning for certain sentences, certain articles, you needed some regular expressions for you to handle all this parsing, and which is very powerful tool. But again, it's kind of harder to understand and extract meaning from those regular expressions. You need to practice a lot just to use those. Julia support per style regular expression. Whatever regular expression you used previously with Perl or even Python, and you can use it here directly, just copy and paste. So there is a online help function. You can use a question mark and directly get you to the help prompt. And I'll show you in a second, but or you can directly use a question mark and the function name. It will print out the information about a particular function for you. Okay. So before we jump into the basics of Julia here, let's get into this channel. I'll show you what I just mentioned. With a question mark, you just need to type in question mark. It'll prompt you to the question prompt. If you just type question mark, that's all you need to do. It automatically changes this prompt into help. Then you type the function name. It'll print out the function, how the function is defined, and what particular function you're looking for. And also it's give you some examples, which is quite useful for you to refer to this and start your programming. But this is helpful when you don't have online help or you don't have internet. You can directly get help from this internal built-in interface. If you have, ChatGPT or some other tools on handy, and you can directly generate all the statement for you, and that's probably reduce a lot of your programming burden. A lot of co-piloting and co-programming assistants that do have a Julia support building, mainly because Julia is open source language, and a lot of codes are available there. And most of language models, whenever they do any training with open source data, Julia codes are readily available. So that's why it's very easy way to promote some kind of language by making all the source code available, and the large language model can just learn from it and generate code for you automatically, which is actually more or less offset some like the user community support somehow, especially for languages like Julian and some other not so popular languages. As long as their code base is online, whenever you get a new user, they can start it quickly by just asking those large language models to help them generate code for them. I'm not saying we have to write everything from using ChatGPT, but it's a good helper, and use it, and especially when you're writing programs using open source tools. Function is a building block for every language, almost every language now. Define a function, you can modularize it, you can make it like atomically helpful. Atomic means it's self-contained. It just do the things you want and need the things you ask it to ask the user to provide. So a function is just like a mapping from A to B, and A here is X and Y in this particular function. B will be the X plus Y. So this mapping function will be simply do the addition for you. In Julian, you can use Unicode like sigma representing the addition function itself. You can define a sigma function, which just like literally sigma here, as a function name to text x, y, and an input, and you can define the function that way, which is quite impressive. So you can use a plus sign as a function operator. Plus sign itself is a function operator. It's a plus function, literally. And then you have a plus function defined as a plus, and you can have a plus function defined itself. So a function itself is treated as a like so-called first citizen of your, how we call the first citizen of your program language. So you're treating function itself as a variable. Then you can pass, you can transfer, and you can do many other things with functions here. You can use the function itself as input for another function. This getting into the domain of functional programming, but Julia itself is not defined. It's not defined itself as a like Haskell and others as a functional programming language, functional programming language itself, but it does support some functions like functional programming. Oh, also, it's pretty common if you see some explanation symbols. And if you are going to chant the argument inside the function, it's good to append the explanation symbol in the name of the function so that others know that you are going to modify this existing function you have been assigned to. So which is it's a common practice. You'll see some examples when you read some online documents and some online examples. You can see people use this programming style. And again, this is another feature very similar to Python. When you write a program function here, you can define positional, so-called positional arguments and keywords arguments, right? Those arguments with some default value could be treated as an optional argument, because even if you don't give the value for that particular argument has a default value, so you don't need to provide any input. So the user is not required to provide input for that particular argument. So that makes that argument itself optional. You may also treat those optional arguments as those arguments that have default values in the definition of the function. So that's the same thing. So you can use this same function to take two arguments, say 1 and 2 here, where the z will be treated will be just simply 0 if you don't provide it. If you provide it, it will replace the last argument for you. So optional arguments make it possible for you to define a single function to handle multiple input. This is particularly important when you're dealing with, say, a function that can work in multiple dimensions. You can take one-dimensional vector, two-dimensional vector, a three-dimensional vector, etc., four-dimensional vector. Given no matter how many dimensions, how many values you have, you may just treat those given values and use the last, say, z value as a default value, which is more or less like which z plane you want to put your xy coordinate. Here, I just want to put my z equals 0. That's my z equals 0 plane for xy in a 3D dimensional space. Now you can directly deal with xy, which is like two-dimensional data set. Don't worry about z, because z by default is 0. But the thing is that for this function, you just need to define it once. So you don't need to define, say, point 3D, point 2D. It will be working for you, just given this value, x and y. Okay. So Python also supports this. So it's nothing new here. It's just, just some feature that I think is good for new program languages, to have. The same for the keywords and position arguments. The only difference is there's a semicolon that is used to separate these unlabeled arguments for you. So keywords can be used to label those arguments. For example, A, B, C here. C will be the argument that it's optional arguments because you have what? You have a default value 1 set to set C to get started. But D here, it's a I would say the position. I'm sorry. This D here is a keywords argument, which is separated with a so-called position arguments with a semicolon. So this keywords argument could be anywhere, and you can put it at the very front, put it at the very end, as long as whenever you want to set a value for D, you need to set D equals something. That's required. But by doing that, you don't need to worry about the position anymore. It's kind of like keywords arguments in Python as well. You have A, B, C, 3 arguments, but if you define those as the keywords arguments, they could be anywhere in your argument list. So even if you mess around with order, the function itself understand which value is pointing to which particular input argument. However, the position argument, because A, B here, they are actually the first, those are the first two arguments. So whenever you give me two numbers, if you don't give me the label, I'll be assigning them to the corresponding, argument list. That's why it's positional, because you need some way to uniquely set those values, either using labels like D equals here, or you use a default index, which is implicit in the sense that that's the first, A is the first and B the second. And that's the definition in the function, right? So gradually, I think more and more people prefer to use keywords arguments. And just like myself, I prefer using keywords. In most of my programs, I don't use the positional. Sometimes positional arguments it's helpful. If you have an extremely long list, probably if you know that everyone will be following this particular list of order, that's fine. But in some cases, it's kind of easy to mess around with order. But if you have this keyword argument, you know exactly which argument you are setting the value to, and that makes it less likely to make mistakes like that. So anonymous function is something that Python is also supporting. It's called a lambda function in Python. And an anonymous function is that you don't need to give a name for the function. You just use it internally. Whenever you define it, you use it. You don't need to give a name to refer to it in the future. If you want some function that needed to be referred to, you have to give a name. Otherwise, anonymous could be anonymous to anything. If you don't have a name or a tag or label to refer to a function, there's no way you can call the function, right? If I don't have a name, you don't know how to call me. You know it's a person, but you don't know how to refer to it. The same here. That's only usable when you have some function that you want to define on the fly, and you want to use it right away, and you don't want to write a separate function for it. Just do it. Just use a anomaly function. You use the syntax is very simple, like the one I'm showing here in the first line. X with a arrow symbol, minus sign and greater. That's arrows. It's not a one symbol. It's just like it's a combination of two symbols. You are defining a function. In a sense, you might treat it like a one direction mapping from x to 2x minus 1. So you have an input x, and this anonymous function will take your x and map that to 2x minus 1, and that's it. Because Julia is a dynamically typed, so this x could be anything. Could be, depending on what value you're giving to it. Could be a vector, could be matrix, could be anything. But again, you need to be careful about the operations you apply to x, which should be acceptable for a certain type. Otherwise, 2x minus 1 doesn't really mean anything. If you have x defined in a very, very weird way, and the 2x minus 1 might not be easily calculated, depending on how you define this x. So an anonymous function is primarily used to fit in other functions. So usually it doesn't really do, because it doesn't need a name. And the dotted function is one of the most interesting features in Julia that I think you may find is very, very useful for you to vectorize your function. What I mean by vectorize is that in many cases, you probably just need to write a function for a single element, say a plus b. Now, what if a is a vector and b is a vector? And I know for sure A and B are the same length. Otherwise, it doesn't make sense to do the vector addition without the same dimension, right? So assume A and B are the same dimension. I can simply add an extra dot symbol, just dot, nothing more, nothing less. I can add an extra dot symbol to my original definition of A plus B, which is only handling scalar A and scalar B. With this function dot, I can use A and the vector, B and the vector, and put them into my function as arguments. And my function will be handle this A and B element-wise. What do I mean by element-wise? So it will automatically apply the function to every corresponding element of all your arguments. If you give me A, B, C, D, E, F, G, consider my function is simply giving me A, B, C, D, F, G. I can add them up. Now you give me A, B, C, D, F, G, and with a dot, function dot, and the Julia will convert this function into a loop. This loop will be iterating through the first elements until the last element of all your arguments, and automatically attach this reference for A and B and C, D, or the E and F to find the corresponding element for the given index. So the calculation will be done for every element. And the syntax is just as simple as adding extra dot after the function and before your parentheses. So in this example, I define my function to be A, times B, right? Now giving me two numbers, 1 and 2. The answer is simply just 1 times 2, which is 2. Now, given this dot operation, I have this 1 and 2 because I have this, my A will be a vector, B is a scalar. The thing is that even the dimension doesn't match, but the scalar itself multiplies vector has its built-in meaning. So what we are trying to do next will be simply multiply a single scalar with the first element of this vector and the second element of this vector. So your result will be a list or array of 3 and 6, because 3 times 1 is a 3 and 3 times 2 is 6. You get a 3, 6 as your output. Now, if you give me a vector with 1, 2, another vector with 1, 2, 3, this multiplication won't work because you don't have a matching dimension. And your results will be, ambiguous depending on the order of multiplication, etc. But as long as you have non-ambiguous, operation defined, you can get that done. Now, if you look at the last one, this is more interesting. You are doing this dot function of 1, 2, and 3, 4. What you are doing next, you'll get a vector. If you apply this function to this 1, 2, and 3, 4, these two vectors, you'll get a 3 and 8, 3, 8. Now you're calculating the signs of the 3 and 8 separately. So you get the results of sine 3 and sine 8 in your final output. You can try this on the Julia repo interface, and all this will be working nicely for you, and you can check it out yourself. Okay, so you can define functions of functions. Let me check if there's any questions. I'm sorry, I didn't follow this. I'm looking to the chat room. Okay, good. So you can define function of functions, and they could be nested, and you can just like the way how you call functions in Python can define functions. You can have a function calling another function. You can have a function calling itself have a has a recursive function call. So the part 2 of this Julia, I'll get into data structure, which are also essential for writing program. There are 2 big components for program. The first one is about syntax, another one data structure. The syntax itself, it's usually for most program languages, it's very, very simple. If you look at the basic structure, you have a statement, you have if-else conditional statement, you have a loops to handle large quantity of data as long as they have a similar structure. You don't need to understand the structure of individual components because they are identical, they're homogeneous in many ways. Even if it's not, you can find ways to convert them into homogeneous structure. So you can iterate them. You can have a loops go around to deal with large amount of data set. So another part is a data structure. Data structure is a way how you organize your data. And as a way how you organize data should be mapped to particular applications. We are dealing with, a data set of a power consumption. You don't want to create a tree structure to deal with it. Probably a tabular table will be sufficient. So your data structure will be just a list. Or, in Julia, it's just array. It's just array of all the numbers organized in a certain way. But if you're dealing with, say, social network, trying to figure out, if A is connected with B, C, or D, well, you don't want to use probably don't want to use a tabular formula, probably a table to represent your data. You probably want to create a graph. You have your edges, you have nodes, and all the things connected like a graph, right? That's a different data structure you're using. So in Julia, by default, you'll have array, you have a tuples, just like a tuples in Python. You have arrays, just like a list in Python. You have a sets, just like a set in Python. You have dictionaries, just like a dictionaries in Python. So if you get into more advanced data structure, you can define graphs, you can define trees, you can define forests, you can define, kind of crazy structure, whatever structure you want. But essentially, two big types. One of big type is just like a tabular form. Dictionary is the simplest table. You have a key pair value, A, B, two columns, right? But again, B could be nested. B could be a dictionary, and again. You can build up a tree structure using a dictionary. But again, it's a very simple tabular format. You can consider what dictionary is. Now you have a graph format which can handle with unstructured data sets, and these two are actually convertible from one to the other. But again, different data structure optimized for different applications. And you can convert different data structures to represent different applications, but you won't be paying some extra price. So just choose the right data structure for the right application is kind of very important thing to think about even before you write a single line of program. Okay. Now, tuple is an immutable arrays. And after you write down the tuple, define the tuple, you can also change it. There are many reasons why you don't want, there's many reasons why the Julia doesn't want you to change it, mainly because if you want to change it, then Julia needed to add some extra things to the memory definition to make sure this memory is not blocked in a certain way. And when it's trying to optimize it, you need to consider some extra rooms for you to make modifications. But if your particular data structure like here is immutable, and on one side, it will make this piece of information pretty secure because it will be protected by the program language itself that your part is not changeable. So you won't be able to lose any information. It's kind of hard for others to hack into your code as well, to just modify this particular piece because it's protected by language itself. The second part is that for performance considerations, for immutable arrays, it's just like a constant list. So I can use that to fill in my memory gaps doing other things because I know it's constant. There's nothing will be changed. So it's my freedom to utilize this feature to optimize the performance for the program. And in many ways, and this is probably one of the main reasons why people use immutable objects, just because for performance considerations. Arrays is just tuples as well, but it's tunable. There are many other features. You can do this and do that, just like what you can do with a Python list. And you can have this is defined with a square parenthesis. Even this syntax is identical with a Python list. You can do the so-called list comprehension. The for statement here is n squared for n in 1 and 5, 1 column 5. It's just like list comprehension. You probably learned from Python as well. It's able to generate the list for you, just reading this statement, which is an easy way to create a new list. And also you can define multiple dimensions. You have the 0s to 3 will generate dimension 2 rows and 3 columns, etc. So you can have different shapes. You can consider this arrays in list like a combination of list and NumPy arrays in Python. It's not simply list; it's optimized for numerical calculations. So it's like a union of list, which is handling some generic list element, and the numerical arrays, which is optimized for numerical calculations. So for matrix and array operations, the dot operation is some of the most useful features you may consider, kind of like an extra feature that Julia is providing. With the dot operation, you can use b dot plus 10. What it does, it will automatically add 10 to every element of this vector b that you're using, or b here is not just vector anymore. As you can see, the definition here, b is a two-dimensional matrix. It's a 3 by 3 matrix. So each element inside this matrix will be will be ended 10, and you can get the results returned to you as a 3 by 3 matrix as well. You can apply the sign function to B, and then because it's a dot operation, so this dot operation will more or less like create a mapping that for every element of this vector B or matrix B will be mapped to a corresponding function that applied on the particular element. So you can get a whole matrix or array generated using this dot operation. You can also do the transpose, which is just a one single, I believe it's a single code, should be just represented, just like the mathematical syntax. That's how you do the transpose. You can do the inverse of B, as long as B is inversible mathematically, this inverse of B will be working. And then you have matrix multiplication. Matrix multiplication will just following the matrix multiplication rules, columns and rows, and then it will calculating the corresponding element for the resulting matrix, and then you get everything done properly. And then you can have a dot multiply. That's simply do the element by one element multiplication. First element times first element, and getting result will be the square of the element, like the one I'm trying to do here. You can also do the dot element for power, etc. So the dot operator is just used almost everywhere when you're dealing with vectors and matrices. So sets are probably defined almost identical to the sets in Python, and you can use sets to help filter out unique quantities, just like the one I used before. I use set to, if I have duplicated element inside my array, I use set for me to get the unique elements out. There are many other operations you can play with the set, like union, intersect. Those are used to find the corresponding set operations, the results of the corresponding set operations, like union, intersect, and then also the difference between different set, etc. Dictionary is similar to Python dictionary, but the syntax is a little bit different. You have, when you define a dictionary, you dict, and then you have instead of using column, you use this arrow symbol to representing the corresponding relationship. Okay, we talk about variables, data types, and then we talk about the data structure, which are like building blocks for programs. And then next will be more or less like a workflow, the flow chart. The flow of Julian language or Julian program is nothing different from other structured programming languages flow. This is like standard structured programming language, kind of like scenario or paradigm when you're trying to write a program. You needed to figure out the step-by-step operation for your particular business logic that you're going to deal with. There's always a start and end. The start is where the program will start, and the end of the program will either print out something or just do some work for you, and then it will quit, and then return the memory back to the operating system. In between, you'll have branches, like if conditional statement, you have for loops and many other things. That's where your real work is done. So for controlling blocks, there are multiple ones. You have ternary expressions with 3 arguments. We'll get into that in a second. And you have a Boolean switching, yes or no. And if a yes do this, no do that. That's like a 2-branch switching. We'll get into that as well. You have a if else, and kind of like conditional evaluation. You have a nested if else if. So this could be built up. You can build a very complicated logic with this if else if conditional statement. For and is just iterating with a given number of iterations, it will end. And the while and is just, it doesn't really care how many iterations you're doing. It just care about particular condition, if it's satisfies or not. And then last, we have a try, catch, error through kind of exception handling, which is common in C, Java, Python, and many other languages. You try this out. If anything happens, I will not quit your program. I'll just return this error to you, and then you'll decide what you want to deal with it. If you want to ignore it, fine, we can continue. But if you want to handle it in a certain way, just do it here. That's try, catch, error through kind of exception handling mechanism. So for ternary and Boolean expressions, let's get started with a ternary expression. Usually has a three parts with a question mark, which we're all trying to evaluate the first statement to see if it's true or false. If it's true, the return will be the second expression. Otherwise, the last expression will be returned to you. Basically, the last expression only returns when the first statement is false. Okay. You can combine the Boolean condition and any expressions using this and also or symbol. You can try, there is a one function called is odd. 41 is odd, of course, so there's a true value. Then you add this print line that's odd. And then you can, with the first statement, to decide if you want to do the second one. If it's a true, and then the second one will be printed out, and then you can print it. That's all. You can try this out on your Julian notebook, on your Julian repo. Conditional statement, it's something actually very intuitive. I think in this part, it's not that complicated to understand. Given any condition, there are always some comparison getting to there. It's either big or small, or it satisfies this or not, etc. If it satisfies certain condition, do this. Else, if some other things happening, do that. And else, if you can have multiple branches of else if, until finally you exhaust, you use up all the possible conditions, and then you have a default statement. Whenever something above are not happening, you do something. That's an else statement. And finally, you have an end to wrap up this loop so that Julia can understand that you're finishing your conditional statement. So that's the whole structure. In some languages like C, you have a switch. You can switch this particular variable. When this variable is 5, case A will be happening, case B will be happening here, case D will be happening there. And that's a switch conditional statement. Switch it's like I would say it's a more organized way to write this kind of if-else conditional statement, because you are only capturing certain cases, and those cases will be handled in a more or less like a parallelized way. It's not like the if conditional statement. You needed to go all the first to the very end, step by statement. With a switch, whenever you evaluate the condition, you can directly go to a particular case and do the continue with execution of the program. There is also an if-else statement. What we're trying to do here is just trying to evaluate the first statement. If the first statement is true, do the first, otherwise do the next one. It's kind of similar to the ternary statement, but it's just easily built into this this statement, and you can do many other things with by integrating this part with this particular if-else statement with other part of your program. So the return value is just the same as like ternary. It's just like the syntax is a little bit different, but it's essentially doing the same thing. The most powerful part for program language is a looping. That's almost guaranteed. And the most heavy lifting part of this of any program is done with a loop, because that's when the computer can easily beat humans. Because for us, we usually feel bored or getting frustrated and doing, when you're trying to repeat doing things over and over and over again. But computer is really, really good at doing all this looping. That's exactly what we want to convert our task into this kind of like repeated patterns. If you are repeating, doing a lot of calculations again and by again, if you do this more than 3 or 4 or 5 times, you probably want to start writing a program. Just let your computer handle it if you're doing this routinely. And this looping condition or looping controller statement will be able to handle that in most cases. So for loop, well, usually needs to know the number of iterations you want to continue. Of course, you can also insert some conditional statement inside the for loops. Whenever those conditions satisfy, you can just break out the loop. It's doable, but it's not recommended for loop. For loops is usually when you know exactly how many iterations you want to go. If I want to iterate 100 times, fine, let's just do a for I in 0, 1, 100, etc. Right? So the one in the middle, the 0, 1, 10 here. 1 is a step, 10 is an end, 0 is a starting. So you start from 0, end with 10, but every time you step with 1. If you change this 1 to 2, you'll be 0, 2, 4, 6, 8, 10, etc. Julia is also working in the same way. Like Python, you're iterating through the element inside a string, you're iterating through more or less like an array of characters. So with that in your mind, it's probably very easy to see what's the outcome of the second statement. When I have the for L in Julian, double quotes, you want to print L with this link, how to call the linking symbol. You can print like JULIA and with this symbol in between. You can get that down. So for loop could be used to do the so-called array comprehension. That's more or less like generating arrays. Like list comprehension in Python, we do the same thing. You can do a enumeration for arrays. You can enumerate. You can have I for I in this enumerator around 3. You can generate a list of array. It can also generate expressions for certain functions, and which is just not commonly used, but you might see that people use that once in a while. It's always a good practice to get everything written in a more explicit way. And also you can have a nested loop. You have for loop with conditional statement, or you can have a loop with void. Consider you have a 3-dimensional space. You have x, y, z. You want to loop through z, y, x, or in other order you want. It doesn't really matter. And then you have nested for loops. And inside for loops, you have a conditional statement. Whenever some condition satisfies, you break. You break your current loop. You go back to the the next layer or next loop, and then you continue with the current loop, and then you break again, etc. So you have a mechanism to control how this loops is continuing or breaking by inserting this conditional statement. That's something we can talk about. Probably there will be another loop here. We'll have some example for the break. So while statement is usually evaluate this information first, then you do the execution. Whenever this condition satisfies, then I do the calculation. But a for loop is first do the calculation and then go back check the condition if it's satisfied. So you can when you don't know how many iterations you want to have. But here this is a special example. You want to go 100 iterations. But in some examples, if you don't know and you need to evaluate some criteria, for example, the error that you are computing, you don't know how many iterations you need to do to reduce error to a certain threshold. So the thing you can use a while loop that can while when this error is still greater than this threshold, I continue doing the evaluation until my error is getting smaller. But again, it's always a good practice to set a breakup loop. Otherwise, you have a dead loop, right? Endless loop. You want to check, say, if this loop is going beyond 1,000 times, and then I'll just break. Or if some certain condition satisfies, you just break. You don't want to continue this iteration until your battery runs up on your computer or there's no power. Otherwise, this loop will be continued if you don't have any breaking condition satisfying this. The exception handling block is pretty commonly used in the production code because you never know if your code will have this error or that error. There could be many, many different scenarios you want to handle this kind of errors. And this try cat statement is the standard way to capture the error and get your error printed out so that you can do this for debugging purpose. Python has the same way. Julia has the same structure, and C and C++ has similar structure, and Java has similar structure. It's just like in those languages, you don't have an end, but here you have an end statement. You want to wrap up this whole thing so that you have a nice structured exception capturing block. So again, this is used for debugging code, and also used for logging any errors your users might be having. And it's kind of hard for them to debug code for you, but they can bring this error back to you so you can check to see if there's any problem in your code. We can help you with the debugging. Okay, so before we get into the last section of this one, oh, actually, this is not last. We have one more. So plotting with Julia, probably this is the last part, I believe, the part 5. Okay, so I have the Mandelbrot plotting this plotting section. Okay, so we have this last part here. So there are multiple ways to do the calculation, and then you can, after your results are ready, you can either plot them directly from your memory, or you can read the files, just plot them out. Usually just, in most cases, you just plot from memory. And because this REPL, R-E-P-L, the command line interface, so the Julian communities have been developing this so-called Unicode plotting functionality, so that you can plot your line graphs or even pie charts or some other figures using this Unicode. It's not as smoothly as you may expect compared to some other fancy plotting routines, but this can give you a first peek about how your data will look like, how they are changing and varying, and you can easily see the trend, etc. So this one, for this particular example, we generate a 5 by 5 matrix, 5 rows and five columns. So each row representing a line with 5 data points for each row. I'm sorry, for every column, it's just one particular for a particular line, because that's a corresponding line. And each row will be each column is just one particular variable, and then you have every row here will be showing the corresponding data points. So it's just a line plot. Just plot out the corresponding x and y value for the corresponding matrix. I'm sorry, for the corresponding line. So you get 5 lines total. And you can also change the color, which is by default, it will be using this color map automatically built in. And you can use a line width, which is 2. So to do that, let's get to the, we start with, since we still have some time today, we can start with the this plot. And let's try to see if we can plot something out. Let's see, I have this already. I already on the Julian interface, and I can copy paste this. And first thing I need to do, I needed to use this Julian, the plots module. It's just like import plots. And this one should be already installed, because when I tried to do the installation previously, I did install plots and Unicode plots. You don't need to install this anymore. Otherwise, just follow the instruction to install the modules for you, packages for you. That's not called modules. The second thing I do, I'll activate my Unicode plots functionality by using Unicode plot. So it will use this Unicode plot as a backend. Okay, when I say backend, you might consider, well, Unicode could be a backend, and some other plotting tools could be a backend. Yes, you're right. And we can have a Plotly and many others as backend. But for the web-based interface, the Unicode might be the only one working here. And you can try other different plot backend. If you have a Julia installed on your local computer, you should have a very beautiful, smoothly looking plots for you. But on this web-based interface, we'll be using Unicode plotting only. So next one, I'll just directly copy and paste this one, this line. Well, it seems there's a little bit, but it's okay. I think it's not that bad. So I have my random number generated. I generate, if I do 5 by 5, you'll see what. So this is what I generate. This is like a 5 by 5 matrix. So it does is take, each line will take this one element. You can see, this matrix will be different because every time you have different seed, and then your random generator will give you different numbers. So I have 5 lines plotted out, and every line representing could be one row here, could be one column. It doesn't matter. It's just either a row or column. But I have 5 lines, each one be showing corresponding data points. So that's how you do the plotting using this. This is ASCII. No, not ASCII. I'm sorry. This is a Unicode. ASCII will be even less, elegant. It will be only using this ASCII code, 256 code to representing plots, which will be something we'll be using next for the fractal plots we'll be doing. But again, it seems to be working fine for me on our portal here. So that's for Unicode plot. You can plot anything, for example, you can plot a sine, cosine, but I'll just leave you all for practicing here. Next, this one is using Plotly, and we cannot show it here, not working with the web-based shell, but if you get Julia installed locally on your computer, this will be working perfectly. And it's also, this plot is interactive. It's very nice. You can move it around. You can use your mouse around. You can highlight. It will highlight individual line, and you can take snapshots. You can dump it into different formats, etc. So that's the Plotly, which is also used in Python for you to create interactive plots as well, if you're familiar with Plotly. There is another framework, or GR framework. It's another backend that is created using Qt. If you're not familiar, Qt is a graphical user development interface. I'm sorry, is a development toolkit for you to develop applications on Linux, Windows, and Mac. It's a cross-platform user interface development toolkit called Qt, which is very, very popular in the open source community. And this GR framework is created using this Qt package, and you can create a nice figure using this package as well. So next, this is a very simple example I want to demonstrate here with Julia. If you are familiar with fractal, and you can probably just switch around with different fractal representation, different examples of fractal instead of using the one I'm showing here. So fractal is refers to geometrical shapes containing detailed structure and arbitrary small scales, and you can zoom into no matter what, because as long as your data is able to resolve the fine structure as fine as possible, but at some point your computer resources will just so limited to stop somewhere. But in many cases, mathematically, you can always zoom in to see all the fine structures. There are some repeating patterns here and there. And after several iterations, you'll see some repeating patterns, very beautiful mathematical work. And also the fractal appears similarly, at various scales, and make it very, very easy to see the pattern like that. So I have a video here. This is a YouTube video. I watched it like many years ago. And this one is given by Dr. Mandelbrot, who first came up with this idea to start his so-called Mandelbrot set. I don't think we have time to go through the details of this, but I think just consider it's a collection of complex numbers, and these complex numbers satisfy certain conditions, and we want to print out this C values of C that when Z remains bounded given this N. So you don't need to be expert on complex numbers and complex analysis. But this procedure to calculate the C should be straightforward by following the rules defined by Dr. Mandelbrot. I'm sorry. And this is a very simple plot for this. And so what do we do? We first define, I'm sorry, let me zoom in this, put this in study mode. So first we define a function. This function is doing nothing by simply doing the square and applies a number a here. This a is actually the c that we are looking for, So what this Mandelbrot function is trying to calculate this, giving alien a, it will be calculating the square of the z starting from 0 plus a and continue iterating. So when I try to detect if my c is limited, is bounded, I just compare my c to a certain value 2 here by calculating the length, or how do you call the length of the complex number, or absolute value of the complex number, by comparing that with 2 to see if it's going out of bound. Because my x is going from 1 to -1, and my x is going from -2 to 0.5, and I want my c, this value c, to be bounded. And then if it's bounded, I print a star, otherwise I print empty space. So by doing that, I'm able to print all these c's, all the numbers that satisfy this condition with this x and y as my coordinate. So that's how you get the Julia version of the Mandelbrot function defined. It's a very simple example. You can do this with Python as well. And let me try run the example on my interface. So I'll control D here. If you get the code, we haven't really copied the code back to the front end. You can go to the slide, let's see which slide, slide 20. So in the slide 20, we have the example hosted under Scratch training. And what you can do is just copy this file to your Scratch space, and then just unzip it and untar it, and you get to the you get into the directory with cd as a change directory, and then you simply just run the example here. So following that, that's what I did, and then I get a directory called if I cd my Scratch space, I got a directory called Julia example created. I'll clean up my screen. So I got a 3 files under it. So the hello world Julia packet is nothing more than just one line of hello world, print line, nothing more, nothing less. That's the hello world you have been learning when you start learning C or Java and Python. Everyone asks you to try it out when you first learning language. And if it's Julia, let me check if I have yes, I have my Julia still loaded. And then I can just run my Julia, and then just type in the script name, hello world. So what it does, the Julia will take this script and import it, and read this bit into the memory and parse it, and then execute it. Kind of like when you have a Python to execute your Python script in the exact same way. Now I have another example. I have a Julia, let's see, Mandelbrot. So what it does is just do a lot of complicated calculations, and then try to figure out if my xy, given this x and y as my how to say my coordinate, and try to evaluate every single point on my window to see if it satisfies certain conditions. If it is, then plot out a star, otherwise plot an empty space. So it's a very, very low quality fractal, but you can see the profile easily with this. Now, what does the code look like? You can use a mol. This is actually this is a whole piece of code that I have here. It's already showing in the slide. And it's just trying to compare, given my x and y, I try to compare this. And the reason, now you may ask me, why I can see all the stars without going out of bound, etc. Because the total number of iterations is fully determined, because I'm going from -2 to 0.5. That's like two 2.5, the total range is 2.5. Divided by 0.03, you are getting up to probably 80. I'm sorry, 3, yeah, 2.5 is about 80. So the total, if you are not familiar with this asking, I'm not sure, can I show you have the total width for the cursor is about 80 something. I forgot the exact number. So that's why I can fully utilize this ASCII format to show up. So this is the reason why you don't see any outbound, because every time when X going to one cursor to the right, it will print out a star, and then the longest string along this horizontal axis here on my screen is about 80 something. The same goes for Y. Y is about 2 divided by 4 is like 40. Like 40 times 80 kind of like resolution. That's what this plot is about. So with that, I want to conclude all the slides, but there is one more thing I want you all to try out. Since you're already logging on our ACES system, there is one example. Actually, this one, I'm sorry, this one is not actually updated with the latest, without the latest Julian function, but Julian module, I'm sorry. So I needed to modify this one. On your end, you don't need to modify here. I can use VIM. If you're not familiar with it, don't use it. It's kind of, you probably have trouble to create it. What I'll do, I'll go to the files. I'll go to Scrat. It will point me to my Scrat space. I can go to Julia examples. And then I can click job script. This one will be like in the view mode. I cannot edit here, but you can click the drop-down menu and then edit. And you can edit using this interface, which is more user-friendly. As I mentioned, we can simply do module load Julia, which will give you the latest Julia, which I think is probably the way it should be. And everything else should be all right. You don't need to change anything else. It's just a CPU code. We don't do any fancy accelerated programming. After that one, after it is done, you can, I'm sorry, you can save it. Assuming it's already saved. And then I quit. Let me double check if it's already updated. Oh, no, for some reason it's not updating. Let me do edit. Wait a second, it seems to be updated, but it's just probably the cache is not refreshed, the session is not refreshed. So this file is already updated, and you can see it's already module Julia. It's not the latest version, but it's the latest version, should be fine. Let me refresh my window here. Okay, I'm sorry. So I need to refresh here. So it's already updated. So then I'll go back to my window. What I'll do s at Julia job. So what I did, I just submit my job to the backend, and the computing knows one of the computer, I don't know which one, will pick up my job and run it. What's the command line to do this? I use qstat, but I think there is a S one, sq-me. Okay, thank you so much. So I just get my job submitted. It's completed with it's running on the CPU queue, and this is my job, etc. I don't use this sq command much. I think sq me. So if it's empty, means it's my job is already done, and that's it. So the output actually is saved here. This particular file is the output for my job, so I can do more. It's just showing my plot. That's my output. That's output on my job. So with that, that concludes the tutorial for Julia today. And again, we are not using any fancy features and Julia is providing, but you can start with some simple test with all the examples I provide in the slides. You can try them out. You can type them on this command shell, just after you run Julia, you can simply try out everything I tried. I type in the slides, and sometime if you get newer versions, if you have a version bump, some of the features might not be supported, but most of the fundamental stuff that we introduce here should be still backward compatible, even with the newer version of Julia. And those are like the fundamental functionalities for Julia. And I don't think there will be, be a lot of changes for those things. But for some libraries, there might be some differences. But for most of the materials we talk about today, that should be consistent, even for newer version of Julia. So good luck with your future Julia programming journey, and hopefully you can write some fancy code and can run on our computer in the future. Okay, I'll be around for questions if you have any, and my email is jtao@. It's my email. Feel free to reach out if you have any questions. And also, if you have any question about the ACES system, and feel free to contact our front desk. We have also the RT support. I have a help at hplc.tamu.edu, and you can reach out to them if you have any question about your accounts and any other things. Okay, I think that's all for today. Thank you all so much.